Okay. So Elon Musk proposed a Hyperloop as a form of transportation that's basically a pair of cylinders that are under reduced pressure. They have vacuum pumps pumping a lot of the atmospheric air that would be inside these tubes out so that there's less air pressure and therefore less drag um, for speeding little capsules or compartment cars that carry people and or things through the tubes. He proposed this as a method of transportation, in particular from San Francisco to Los Angeles and from Los Angeles to San Francisco across most of the state of California. And I was curious how much volume one of these tubes would have. I'm curious how realistic it is to actually keep a large pressure differential between the outside and the inside, and for that I need to know what volume is. And this is a great exercise in volume of a cylinder. So I can use volume of a cylinder as pi times the radius squared times height, and you can actually idealize this entire tube as being one giant cylinder with, according to him, a diameter of 2.23 meters. So Mr. Musk says that that's the inner diameter of the tube, and that the length of the tube is going to be 563 kilometers or 563,000 meters. So if I divide this diameter by 2, I get the radius, and then I can substitute that into the equation as I can the meters, the number of meters of length, or height, if you think about this as a cylinder. So you multiply these things together, meters times meters times meters will give you cubic meters for the units. You'll get this number as the raw output from a calculation. And these numbers don't have that many sig figs. The numbers that I wrote down here has 7 sig figs. Each of these just has 3 sig figs. So for significant figures, what you're going to have to do is round to 3 significant figures. And that would mean that you'd round to this 2, this 1, this 9. So those 3 digits will end up being significant figures. And you round it, and the easiest way to write it out would be to turn it into scientific notation. So I move the decimal point from here 1, 2, 3, 4, 5, 6 places to the left. So I'm making it smaller. This number is 10 to the 6th, or 6 factors of 10. 6 orders of magnitude smaller than this 2 million number. So I have to multiply it by 6 factors of 10, or 10 to the 6th, again, to make this entire expression the same size as this entire expression. So this is the answer I came up with for the volume in cubic meters for the Hyperloop. And for me, this is not a terribly useful number because I don't have a good mental grasp as to, I don't have like a good feel or intuitive understanding for what a cubic meter is. I mean, I can think of it as a giant box, but it's not something that I can hold in my hand. I'm used to liters. I drink in liters. You know, I have a 2-liter bottle at home of cola that I drink. I drink too much cola, but that's neither here nor there. So I understand what that means. You know, if you go to the convenience store and you buy a 1-liter bottle, you know what that means too. So I'd like to convert this from meters to liters, cubic meters to liters, so that it's easier to understand intuitively. How I think about a liter is that it's a decimeter cubed. So 1 decimeter is 0.1 meters. I know these two things by rote. I memorize them. So I can use these two equations to create conversion factors that I can apply to the number, and then I will end up getting the right units, and I'll be able to convert the number part so that the entire expression isn't any bigger or smaller than the expression that I started with. Okay, so how do I get this thing or this thing into liters? Well, first I write it out again, and then I'm going to use unit conversion techniques to manipulate the units. So I want to get rid of these meters. So of these equivalent statements, this one has a meter in it, so I know I'm going to have to use it. And I'm going to put meters in the bottom, and I'm going to put decimeters from this expression on top. And in doing so, I'm going to be canceling out meters. I have to do it 3 times, or cube it, put it to a exponent of 3, because I need to cancel 3 separate factors of meters. So that's why these things have cubic or 3 exponents. The meters cancel out, leaving decimeters cubed. Isn't exactly what I wanted because I wanted liters, so I put decimeters cubed down here from this equivalent statement. That means I have to put liters on top. And then I multiply and I cancel the decimeters cubed, and I'm just left with liters. So basically what I'm doing is I'm applying equivalence statements or equivalence expressions as conversion factors. So I'm saying, well, if this is equal to this, then I can multiply by this side divided by this, since it's basically the same as multiplying by 1. I'm not changing the size of anything. So that's what I just kept doing in a sequence so that I could get rid of the units I didn't want and eventually get to the units I did want, liters. When I do this, I end up getting a bunch of numbers. This is just like the either 2.198913 meters cubed or 2.20 times 10 to the 6 meters cubed. The number we started with times 1 times 1 times 1 times 1 on the top. And on the bottom, remember we have to divide by every number thing that's left over here. So I have it being divided by 0.1 3 times, and then multiplied by 1 or divided by 1, which is, again, multiplying by 1 or dividing by 1 doesn't really matter. So I'll end up having this expression when I consolidate it. And to get rid of, or to combine these exponents, what I'm going to do is I am going to move this 10 to the negative 3 to the top and combine it. So in doing that, all you really have to do is subtract whatever exponent was in the bottom. So that's going to be 6 minus the exponent that was on the bottom, and that's negative 3, so it's going to be minus negative 3. So 6 minus negative 3 is the same as 6 plus 3, and that's 9. So this is the answer, 2.20 times 10 to the 9th liters of volume. This is a big number. It's actually 2.20 billion liters. Billion with a B. Like 10 to the 9th. Like billionaire kind of billions. Billions. Ooh. So that's a lot of volume. It would be a big project if it ever happens. And I intend to next look at the moles of gas that would be displaced by doing this, and then we'll look at the mass. I hope this was a fun use of geometry and cylinder volume calculations that is important in real life.